All right, it's really great to be here. Thank you very much for the warm welcome. All right. Oh, I probably have to unlock my laptop. All right, there we go. Okay, I'm here to talk to you about running machine learning applications on Kubernetes using a platform called Kubeflow. My personal background is in natural language processing, so that's the lens we're going to be viewing things from today. But a lot of the concepts are much broader, and they apply to most any machine learning application. So a bit of context. I have a few housekeeping items. Context on myself. So I'm Michelle Casbon. I'm an engineer at Google. I'm based in San Francisco. I've been there since the beginning of the year, and I've been working on the Kubeflow project ever since. Well, prior to that, I was at a startup called Cordoba, where I was director of data science, building machine learning applications on Google's Kubernetes engine. And prior to that, I was a data science engineer at a different startup called Idibon, and I was building machine learning applications on AWS. For about a decade before that, I was a data engineer working in the enterprise. So that gives you a sense for my background, where I'm coming from, and why I was really excited to start building a platform that basically gave me the tools that I never had when I was building things from scratch. So a couple of the things that we'll talk about. I want to go over some of the biggest challenges in building machine learning applications and how they've informed some of the project goals. We'll take a look at what's inside, what comes in the box in a default Kubeflow install. And we'll see it in action, and then we'll wrap up by talking about what's next for the project and what's on the roadmap. So, requisite disclaimer slide. Before you start any machine learning project, there are two questions that you should ask yourself. Number one, do you have a very clearly defined problem? And number two, is there any way that it can be solved in a deterministic way? Because if there is, that's what you should do. Machine learning is not always the answer, despite what you may have heard on the internet. And if my decade as a data engineer taught me anything, it's that counting things is still really hard. So let's look at an example of a very clearly defined problem that can't be solved in a deterministic way. Well, we're going to build an application together today, and that was inspired by one of my favorite NLP researchers from Stanford. So he wrote this book, The Language of Food. It's very approachable. It doesn't go too deep into a lot of the implementation details, but it does explain things in a very interesting way. Now, Dan Jarofsky's done some really sophisticated research on the language behind food. Our application is not nearly as sophisticated. It's very straightforward. And what we're going to look at is identifying sentiment for restaurant reviews. So given a review from Yelp, determine whether it's positive or negative. We're going to be looking at a lot of code. Don't worry too much about it because it's all on GitHub. You can view it afterwards with all the instructions for you to run it yourself if you'd like. But we'll start off by looking at, so I prepared a recording today because we're going to be training some models and provisioning nodes. A lot of that has some dead time. And watching neural nets converge is about as exciting as watching grass grow, so I thought I would spare us. We're going to start out with the application that we intend to build. We start out with a deterministic approach. Well, this is a very simple, there's a Flask app, and what we have here is a review. The ramen was awful. It was bland and mushy. And after a few bites, I couldn't handle eating anymore. So really straightforward, something that you would find on Yelp. And we have a button for predicting the sentiment. Now, what's powering that button right now is a JavaScript function where we look at the group of words. We have a list of negative ones. If we find one, we mark it as negative. If we don't, we mark it as positive. Very straightforward. And if we run that function against this review, we get something that's not very accurate. It's not very useful. This is something that machine learning can do much better because we can expand that list of negative words to our heart's content, but we'll never get up to 100% accuracy. We'll always have some sort of gap because of the way different languages work, and sometimes the negative words are at the beginning of the sentence. Language has way too much nuance. So we can do better. Let's throw some machine learning at it. Instead of starting from scratch, we're going to use a platform, and that's what Kubeflow is for. It's a curated set of compatible tools and artifacts that lays a foundation for running production machine learning apps. Kubeflow enables consistency across deployments by providing Kubernetes object templates that bring together disparate components. Throughout the talk, I'll be referencing several different layers. We have our application layer. That's the sentiment analyzer that we just saw, that UI. And then we have our Kubeflow layer. These are all the tools that enable us to build our application. And then we have our infrastructure layer. We have our servers. This is where our Kubernetes cluster lives, our storage layer, and any services that we're accessing throughout the platform. And what you'll see up here is this little icon. And most of it will be grayed out, but I'll highlight the sections that I'm talking about to make it a bit clear about which section, which layer we're referring to. OK, with all that out of the way, let's look at some of the major challenges in building machine learning applications. I want everyone to visualize their favorite piece of production code. You know the one I'm talking about. It's out there running, it's doing something very well defined, doing its thing, doing it well. Maybe you wrote it, maybe you didn't. But think about how it got there. It wasn't conceived in production. It didn't just appear there one day. It came from somewhere. Maybe a staging environment. How did it get into that staging environment? A dev environment, probably, hopefully. At some point in that process, there was a human pressing keys in front of a computer. And every time you move code from one physical environment to another, you introduce risk. Our friend, the forklift driver Klaus, he's familiar with that risk. He knows that moving things from one environment to another can introduce death and destruction. It can be kind of scary. So what we need is a solution that gives us portability, that allows us to forklift our code from one place to another, even if that's just from local into production directly. Something that gives us some portability. And we don't just want to move our application, but we want to be able to package all of those infrastructure components together to reduce the variability, to reduce the risk. Because there's a fundamental difference between running code on a laptop versus in production, in a data center. Another big challenge is complexity. You get all those pieces running together, and it can turn into a big ball of mud. So think back to that piece of production code that you had in your head. If it was a machine learning piece of code, it probably looked something like this. And we tend to have this outsized vision of the machine learning components in our system that doesn't always reflect reality. Usually it looks something closer to this. There are a ton of different components that support those machine learning pieces. Before you can even think about building models, you need to have some data. Generating that data, ingesting it, exploring it, slicing it, separating it between training and test, transforming it. All of that takes a lot of code, a lot of work. Once we have that, we can turn it into a format that our models understand. We extract features from it, take things that are going to inform our predictions. And once we've built our models, we have to do something with them. Hopefully we're validating them, but we're storing them, we're auditing them, we're versioning them. And if we have a model that can't run on a single node, we may be spraying that out against several nodes. Updating it every time there's new data. All this takes code. Those models live somewhere. They live within an application. This was our Flask app. This was our restaurant predictor. And that can involve a ton of business logic. You have a UI, you have to load balance. That application, it also has to live somewhere. It lives on a platform. All of the components that support that, like monitoring, logging, any CI/CD components, there's a lot involved. So that little model building piece, it's just one of many. So what we want is something that can support all of that complexity and allow us to form these smaller logical groups that we can then sort of turn into these modular components that we can reuse. That's important. We have all of those different pieces coming together. It's hard to maintain. This may seem obvious because this is sort of a generic software development conference, but in the machine learning world, like all of this stuff is pretty new, and we don't really have the tools yet for maintaining these complex systems because machine learning applications have a very different footprint. There are different pieces, and the resource requirements are there's so much more variability in it. Just being able to discover errors, to identify it when they come up, is not always straightforward because neural nets can be complicated. We don't always understand why they make the decisions that they make. So once we can find errors, can we recover from them? And can we prevent them from happening in the future? Not all errors are preventable. We still don't know how to solve bias in our models. If we can identify it, and if we do have a solution, how quickly can we patch it? And can we roll back to versions that didn't have that bug? What we need is something that can shorten that development lifecycle, that can automate much of these processes, similar to the way we've resolved that in traditional software development. Capacity planning is huge because of that variability in resource requirements. So the usage patterns, even the ones that we can identify, the common ones, so the one that our system that we always see, even those can be very hard to work around and accommodate. But when the demand spikes, whether that's receiving more data or receiving more requests from the user side, that can be challenging to accommodate. And being able to utilize your resources efficiently is non-trivial with machine learning. So what we need is something that's scalable. Kubernetes handles a ton of that, so we want to run on top of Kubernetes. And we want something that can automatically provision nodes so that our application doesn't have to think about it. It just requests resources and it receives them. They become allocated. So those challenges are some of what's informed the main goals for the project. Fundamental to the Kubeflow project is to make it easy for everyone to develop, deploy, and manage portable, scalable machine learning everywhere. So portability, very important, not just our application, but the entire stack. We care about scalability. This is why it's native to Kubernetes. This is what allows us to reduce the variability between our physical environments. And not just that, but between our microservices as well. We don't have to care about where services are running because we can just call it by name. We don't have to worry about ports and any of the networking details. So third is composability. We want a way to put it all together, wrap it up, tie a nice neat bow on it, and reuse it, and use it for very common processes that you see a lot in machine learning. And we don't want to just support the production instantiation of that application, but the full product lifecycle, from exploration, development, all the way through to production, and then patching and maintaining it over time. What's also important is specialized hardware, like GPUs and TPUs, because if you know what you're doing, you can use these for training, reduce your costs, and improve your model performance in ways that you couldn't otherwise. So Kubeflow is entirely open source. You can find it on GitHub. It has been from the very beginning. And it's for anyone who's involved in the creation of machine learning applications. We have a quarterly release cadence. The most brand new release branch is what you'll see today. It's the 0.3.4 release. And it's still a release candidate. There might be a few rough edges, but we should be rolling a new one pretty soon. We'll be moving to the 0.4. And fundamental to Kubeflow is that it runs anywhere you run Kubernetes. That could be Google Cloud. That could be your own cluster on-prem, Minikube, wherever. It uses open source Kubernetes APIs to manage some of your machine learning tasks, some of the common ones. And it does this by providing custom resource definitions for doing things like distributing your training. It adopts some of those Kubernetes patterns, some of those familiar patterns like the model of having loosely coupled microservices and managing your infrastructure declaratively. Kubeflow uses an open source tool called KSonnet, which is essentially a templating language for Kubernetes. And this is how we can package things up and move them from one environment to another. We have support for lots of different machine learning frameworks. TensorFlow and PyTorch are the ones we see most commonly used, but you're welcome to use whatever you'd like. Now let's take a look at what's in the box. So you may still be asking yourself, okay, what exactly is this? Well, it's a framework for running machine learning frameworks on the Kubernetes framework. You get the idea. This is why we have the layers at the top in the icon. So let's revisit our definition slide. It's a curated set of compatible tools and artifacts that lays a foundation for running production machine learning apps. It enables consistency across deployments by providing Kubernetes object templates that bring together all of these disparate components. Okay, so here's a diagram. Everything in blue is what was added since version 0.2. We start with, so there's a lot behind this. I've just lumped it together into a general ingress container. I think there was a talk earlier that went into a lot more detail. Kubeflow supports a lot of that, but I'm just going to call that ingress. We have things like Ambassador, which is a reverse HTTP proxy, and this provides a single point of entry into your cluster, which means that you can map out a single external URL, and then you can route it to anything running inside the cluster. So from there, we have our central dashboard. You can think of this as a single pane of glass where all of the UIs for each of the internal components, it sort of collates all of them together and gives you a place to access it. So Jupyter Hub, we have this for running notebooks, and a TensorFlow job dashboard for viewing statistics about the jobs that you're running through the TensorFlow job operator. And there's also these 3 new components, all UIs. One of them for Argo, if you're not familiar with that. It's a Kubernetes native workflow engine. We have a hyperparameter tuning component called Katib. This is new. It was based on Vizier. If you read the white paper a few years ago that Google put out, it's a method for performing hyperparameter tuning. And we'll see that later, so I'll explain a little bit more what that is if you haven't done that before. And then our pipelines dashboard. So this uses Argo under the hood, but it's a way of creating workflows from Python. There's a nice GUI. There's a lot of kind of goodies. We'll talk about that a little bit later. But each one of those components has its own, has corresponding controllers that execute everything that's happening that comes in from the front end. And then we also have job operators. We have one for TensorFlow, one for PyTorch. PyTorch is pretty new. I believe it existed before, but one of the big changes is to bring it up to speed with TensorFlow. So there are a lot of common processes between the two, and there's a lot of common processes between the two, and so we've brought the APIs in line with each other so that when you're writing code in one, it makes sense. They're sort of in line. Now, this is not the full suite of components. There's a lot more that you can sort of install on your own, but this is part of the default install. Okay, so click to deploy is one of the most exciting things, particularly for me. This is brand new. It was something that was added very recently, and this is a way to deploy a cluster entirely from a GUI. So I used to have to do this manually, and it was a total pain. So we're going to start out from an empty Google Cloud project. There's nothing in here. We don't have any clusters. You'll see it's totally empty. But we're going to go to that click to deploy tool. It's an open URL. Anyone here can visit it. And what it's going to do for us is basically set up an entire Kubeflow cluster for us. So we enter in our project name. And we're going to skip IAP. What that does is it generates an external URL, which we're not going to use. We're just going to port forward into our container, into our ingress. But that's it. We specify the release branch that we want, and we click create deployment. So what that's doing is, behind the scenes, it's generating all of the objects that we need. That includes project permissions to enable APIs. That means creating service accounts, generating all of the objects, so the cluster itself, and deploying all of the Kubeflow manifests onto it. So here, we have a brand new, nice, shiny cluster. And if we take a look at the workloads, we'll see that Kubeflow is actually being installed into the cluster. This is significant. I don't know if you've ever tried this on your own, but it is super painful because there are just so many pieces. OK, so that's click to deploy. That's one of the new things as part of the latest release. But what else is new? Not just a GUI deployment tool, but there's also a command line tool. That's kfctl. It's sort of an analog to kubectl. And that does something similar. But you'll notice that click to deploy right now is just, it's very specific to Google Cloud. It uses Deployment Manager, which I'm not sure if that exists on other clouds. But the command line tool, that's where you can use whatever backend you want. And it splits up the cluster creation from the Kubeflow install so that you can make changes in between. You can script all of this out. And when you're creating your environment, you can customize it to whatever you need. Now, auto provisioning is also a really neat feature. It's actually a GKE feature, but it's important for Kubeflow because it's a beta feature. But it's important for Kubeflow because it means that when we're running jobs, we can just request resources. We can say, give me a GPU, or hit me up with a bunch of CPU, and we don't have to worry about what's available in the cluster. And likewise, when that job finishes and that request disappears, all of those resources get spun down. They don't exist, which helps with your billing and utilizing your resources more efficiently. A couple of the other things that we talked about, Argo. This is that workflow controller. This was developed, I think, by the Intel team, and it's, again, Kubernetes native. It's not only a workflow operator, but there's also a really cool CD tool. They have something called Argo CD that lets you It lets you basically install Kubeflow and maintain Kubeflow in a continuous delivery situation, but also your own application. You can sort of use that custom tool. And has a Kubeflow integration, so native to the platform. And then PyTorch, we talked about that. There's a lot of ongoing development in that space, as well as TensorFlow. That development is ongoing. Hyperparameter tuning. So the new thing is a study job. So we'll look at that in our demo. We'll see that in action. But the idea behind hyperparameter tuning is that if you have, a lot of times we'll have a model and there will be certain parameters, like the number of layers or the optimizer that we want to use. And in order, we don't really know which parameters to start with. But we'll start with anything, and then as if we run that training job several different times with different parameters, we'll get different results. And hyperparameter tuning is sort of an umbrella term for running that training job over and over again and swapping out different combinations of parameters. So the Kubeflow component basically lets you give it limits. So like, I want to explore this parameter within these limits, and it will run all those jobs for you and keep track of it and help you more quickly determine the best set of parameters. So there are a lot of people really excited about that. We'll take a look at it. And then there's pipelines. The Kubeflow pipelines was probably the biggest release, the biggest part of this most recent release. And this is a way of running our end-to-end ML workflows. So not just a single job with training and serving and any post-processing, but the whole life cycle. So running training several times, seeing how it changes over time, seeing when things get updated, basically keeping track of it, being able to monitor it, and orchestrating that between different pipelines, being able to reuse some of those components, and being integrated with all the other services, both within Kubeflow and throughout your platform, your infrastructure. There's a Python SDK, which means that you can create libraries, so it makes it a lot easier to share and to operate from within a notebook, or just generally within an IDE or a GUI. And yeah, so we'll see a little bit more of that as part of our demo. OK, I've talked a lot about it. Let's see it in action. So this is what we saw before. This is after a click to deploy. This is what we have. It's an empty cluster with Kubeflow installed. This is the default installation. And again, all of the code is out on GitHub. The first thing we'll do is we'll run our training job. So what we have is some TensorFlow code that would normally run on a single node. But what we do is we send it to that TF job operator that Kubeflow provides, and it splits it up. It turns it into a master, a TF master, a parameter server, and several workers. And we can configure how many workers. In our case, we'll have 3. We'll run that against CPUs, and then we'll switch over to using TPUs. So a tensor processing unit, if you're not familiar with it, it's a hardware accelerator that was built specifically for Google data centers. It's a network-attached device, which is distinct from GPUs, which are attached to a physical node. We'll talk a little bit more about that when we use it. Once we have a trained model, we create a container for serving it so that we can call it for predictions. And then a UI, which is that website that we saw for interacting with those predictions and seeing them. And from there, we'll move into a notebook that's attached to GPUs, and we'll do some customization of our model. And then we'll go into we'll create an example pipeline also using GPUs, and then we'll perform hyperparameter tuning. All right, so here's our cluster. We have everything installed, all of the default Kubeflow components. And we can list those. We can see what's in there. So we have, this is everything that we had on that chart. But we have a few extra things. So we have a serving component, a UI component, and then some training jobs. We're using something called Tensor to Tensor, which is a library of pre-configured TensorFlow models. And we're running the same code, but we have it in 3 different versions. We have one that runs on CPUs, one against GPUs, and one against TPUs. We'll run the CPU version first. Well, this is our case on it tool. We're running an apply command, which generates our manifests and applies them onto our cluster. As simple as that. If we take a look at the pods, because we just applied it, we should be able to see all of the different pieces running. Here we go. So we have, just like on our slide, we have our master, parameter server, and 3 workers. So we'll take a look at the logs. and see what's going on inside. And this should look familiar if you've used TensorFlow code before, but it's pretty slow. So we'd rather run that against TPUs. So we'll run the same command, it's running the same code, but it's running it against TPUs. And we'll take a look at the pods it creates. Now this is a little bit different because we're distributing it to our hardware, to our TPU, so we don't have extra pods. It also says that it's pending. It doesn't kick off right away. Remember that we talked about TPUs as being network attached. So what we've done with our case on it apply command is we've issued a resource request. So we've said, I would like a TPU attached to this pod, please. And what happens is in the Google data center, we issue a request, and that piece of hardware running in some data center in maybe Iowa somewhere gets attached. And we can then access that piece of hardware. That takes a little while to spin up. But this is distinct, again, from GPUs. And this is important because it means that we're only paying for the use of this hardware for the duration of our job instead of for the lifetime of the node, like you would with GPUs. OK, so it took us about 5 minutes in this case. And now we can watch it running. Again, same code as running against CPUs, so it should look pretty familiar. But it'll be quite a bit faster. Yeah, this looks much better. So you see a few of the TPU-specific commands. Those logs kind of scroll by quickly. But we'll take a look at the numbers. We'll look at the speed in more detail. So first we'll look at the numbers with a CPU, and then we'll compare that against TPU. All right. So obviously this depends on the type of code that you're running, the type of job that you're doing. There are inefficient ways to utilize TPUs, of course. But in this particular case, we see about a 10 to 15x speed up. So that's pretty good, considering it's the same exact code. Okay, now that we have a trained model, we're going to add our serving and UI containers. So it's our familiar apply command. And we can view these pods being created. We'll check our workloads tab. We have 2 new pods, and those will take a bit to spin up, but we didn't request any specific hardware, so they're pretty fast. Okay, so we have serving and UI. So now that we've created those, we've port forwarded into our cluster, so we can access them directly. So we're going into our UI container. Well, this is the same thing that we saw earlier, but now instead of running locally, now it's running inside our cluster. So this is our naive function. This is that JavaScript function that we saw before. Now we're going to point it at our serving container, the one that's running inside of our cluster, the one that we trained, the one that's providing predictions. And this, see, it's much more accurate. OK, but so what we used to generate that was an off-the-shelf model. It was tensor to tensor, pre-configured. If we want to do something a bit more, if we want a bit more control over that, let's say we need higher accuracies, or we just want to do something a bit more sophisticated, this is where we might do a custom model. And to do that, we'll go into our Jupyter Hub instance. So to get there, we go to our central dashboard. And we'll just quickly show you what the TF job dashboard looks like. These are the 2 jobs we just ran. These are some details about it. But what we really care about is Jupyter Hub. So we connect there, and we can spawn our own instance. So we're choosing TensorFlow 1.7, one with support for GPUs. And we're requesting a bunch of memory, way more than I have on my laptop, and we're requesting 2 GPUs. So when we click on spawn, what that does is behind the scenes, it's creating all these resources within our cluster. And we can see that happening. So we can see a new pod. That's my pod. And if we click on it, we can see that insufficient GPU. So what's happening here, so we requested GPUs, not TPUs. But if you see right here, it says it triggered a scale up. Now, this is node auto provisioning. This is the Kubernetes feature, the GKE feature that if you request something that the cluster doesn't already have, then a node will automatically be provisioned for you, and you don't have to think about it. So imagine that any data scientist can just request whatever resource they need. You can set up your cluster to have limits to that, obviously, so that your billing doesn't get out of control. But we started with 3 nodes, and now, because we've requested GPUs, you'll see another node was created. We didn't have to think about that. And now that our node is ready, take a look at our pod. Our pod started pulling the images, and here we go, it's running. And now we can use it. That means we can access a notebook with all of these extra resources that we requested. Now this familiar Jupyter Hub interface, there's nothing really custom here. You can customize more of this if you'd like. We're just going to use a sort of standard Yelp notebook. And Kubeflow publishes images that you can use, but you could also specify your own. So in this case, we have the option between Python 2 and Python 3 kernels. We're going to make sure that we're running the right one, Python 2. And then we're going to run everything. This particular image that Kubeflow publishes is missing a library that we need. So the first thing we do, we have the ability to pip install whatever we need. So we do that, and then we download that data set, all of that Yelp data. So all those reviews that powered our very first model. We download that, and we load it up into memory. You can imagine that, that this sort of interactive, usually people will use a notebook kind of separately from the rest of their application, but having it in the same cluster means that you can access in-cluster resources. You can have persistent disks so that you can share data between notebooks. And lots of really interesting features that are not part of Kubeflow yet, but the plan is to integrate a lot more with notebooks. So we've sliced off 100,000 from the top, and we're separating those out into positive and negative sets of words. I think there's 5.5 million, which is just way too many to be working with in a notebook, but we could because we have the resources for it. So we can view the histograms for each of those groups, do some exploration with it, and build our one-hot encoding vectors. We won't go into too much detail. If you want to run the whole notebook, you can. It's out there. But this is how we would generate a new model and then swap it out for that tensor to tensor one. OK, so what we want to do now is look at a pipeline. So this is what you see when you first go into the pipelines interface. There are a few samples in here. You can take a look and run any of these. They work out of the box. But what we're going to do is generate our own pipeline, and we're going to run GPUs with it. Oh, I mentioned that there's a Python SDK. So the way we're going to do that is we'll switch to the console, and we have a Python file. We'll take a look inside where we're defining each of those steps. So we're using the SDK, and we have a training step, a post-processing step, and here we are. We're defining our pipeline as just those two. And this, the SDK allows you to basically just run that file, and what it generates is a tar file. Inside that tar file, there is a bunch of really complicated YAML that the SDK is translating into Argo speak. So Argo knows how to run that. Argo has its own sort of YAML format that it expects. But we can take that tar file and upload it directly into the UI. So that's what we'll do. And then we'll watch it run. So if we upload it, it knows what to do. It can interpret everything inside. And we have our two steps. So we have a few different parameters. And we want to start an experiment. And then we want to kick off a run. So an experiment is lots of different runs together. So you can see how things change over time. And we're just taking the default parameters. We don't really know what the right values are, so we're just going to run it as is. Now, this is an example that's using GPUs, and enough time has passed between the last GPU job that we ran and this one, so those nodes have disappeared. So we're going to check to see what's happening. When we created that run, it created a pod, and that pod requested resources, requested GPU resources. So we can see our pod. It's unschedulable because those GPU nodes have disappeared. So if we go and look at our nodes, auto provisioning will create a new one for us. And once that's ready, then our job can run. So all of this is happening sort of behind the scenes, and all you have to think about is what's happening in the pipelines UI. That generally, you don't usually have to pay much attention to that. So now our job kicks off, and we can view the logs. We can see the output. And you'll see that what we care about here is this validation accuracy. That's pretty low. 0.11, that basically means that 11% of the time we'll get an accurate prediction. We could get better results by just flipping a coin, so this really isn't a useful model. Well, this is an instance where we would want to, because we just use the default parameters, this is where we want to go and perform some hyperparameter tuning to figure out a better set of parameters. So this is where we go into our COTIP UI. And I talked about what's going on behind the scenes. We're essentially defining the parameters that we care about, the metric that we care about, and the parameters and the boundaries for those. So there's an example that you can find in the Kubeflow repo. That's what we're going to create. What that does, we're just applying that to our cluster. And what that looks like, it's called a study job. It's, again, a custom resource definition. But if we look inside, we're defining our metric. So it kicked off 3 different jobs right off the bat. And up here, all right, so here's our metric, validation accuracy. That's what we care about. And we care about maximizing it. So we've defined those. And then we list the parameters that we care about. The learning rate, we've said we want it to be somewhere between 0.01 and 0.3. The optimizer type. And I think the number of layers was in there as well. So we already have 3 jobs running. And remember that each of these are running GPUs. So if we take a look, our UI has, it's seen that these jobs are running, and it's collecting all the information. So you can see the 3 parameters that we're looking at. But those jobs take a while to run. It's running a full set of training for each one of those jobs. So that's going to take a while. And as those jobs start completing, we'll see values in this chart. We'll see validation accuracy filling in. So let's take a look at the nodes. So auto provisioning, because we requested, because we kicked off 3 jobs where each of them are requesting GPUs, we've created 3 new nodes, all with GPUs attached. And if we take a look at our UI, a few results have come in. One of them good, one of them not so good. But we want a few more, so we're going to wait until we have about a dozen. All right, so we can do something with this now. A lot more results have come. So what we see here is we're looking at the validation accuracy column. We see a few that stand out as very low against others that are very high. So we're looking for commonalities among those. And it looks like they're all following the regularized leader. So we don't want to use that optimizer. So we're going to clone that pipeline job that we already ran, and we'll use a different set of parameters. We'll get rid of that optimizer. We'll try something different. We'll increase the learning rate and use gradient descent. Stochastic gradient descent is very common. It's a pretty safe choice. So if we run that, it's running the same job, but just with different parameters. And we can view the logs for that container as well. All right, so this already looks better. It's at the very beginning of the training run, so I would expect it to improve. But it's already at 76% and like 80, 84, 86. That's much better. That's an actually usable model. So that's why hyperparameter tuning is kind of so exciting, because you don't have to run all these training jobs separately and keep track of all the results. And in that UI, there are different graphs that you can add to make it even more obvious, especially if you have lots of different metrics that you're tracking and a lot of different parameters. It can get a bit tangly. So there are lots of different ways that you can visualize that. All right, so don't just take my word for it. If you want to run any of that yourself, there's a couple of options. Deploy.kubeflow.cloud, that's that click to deploy thing that we saw. You can give it your own project name, and you too can have your own Kubeflow cluster. Codelabs.developers.google.com, there are a few different walkthroughs there, and you can use that, again, on your own project. Quick Labs will actually give you the resources you need. Katacoda, same thing. If you just want Markdown and you want to walk through it on your own, that's there as well on GitHub. So where is Kubeflow headed next? What does the future direction look like? So with a quarterly release cadence, our O.4 is coming out within the next few weeks. We'll have the first release candidate. And we'll probably finalize that just after the holidays. But the intention with our O.4 release is to get ready for that 1.0 release. And 1.0 is really designed for some of the enterprise features that people expect, like APIs that are supported long-term and we don't expect to change. I think by the time we get to 1.0, we'll have had enough people using it that we feel pretty confident about the decisions that we've made. Another important thing is for ingress, so identity access management and security. So not allowing access to all of the components in a cluster, but just very specific ones, giving people more granular control. And providing a really clean upgrade process. So good CI/CD processes in the machine learning space are hard to come by. But we want to be able to support that, and we want to sort of push the boundaries of that. And adding more notebook integration. So from that notebook, during that exploration phase, we want to be able to run pipelines. We want to be able to kick off TensorFlow jobs, lots of different things so that a data scientist doesn't ever have to get down to that sort of console Kubernetes level. It's not really realistic to expect everyone to understand all the Kubernetes details, but we still want you to be able to build machine learning applications. And so moving towards more notebook integration and generally a more UI-centric workflow. So along with that, lots of new features in the pipelines UI. You can expect to see a lot of changes in that interface as well. And being able to manage your models, so storing them in a central location, versioning them, auditing them, sharing them among your team, your organization, the world. And then adding a lot of test infrastructure, so supporting a good CI/CD release process. Now, if there's something that's missing from this list, please speak up. We're happy to include it, maybe not in O.4, but in a future release. Because Kubeflow is not just open source, but it's very open in terms of community and ideas and design. So if you'd like to get involved, join the Slack team, join our calls. We try and keep them at times that are friendly to different areas. We're a very global team. We have a lot of people, a lot of contributors in Asia. We have some here in Australia. We had our contributor summit just a few months ago in Sunnyvale, and there was someone attending from Sydney, like via Hangouts. So we're not just supportive, and plenty of people flew in as well. There are about 70 people there. But we have a live stream for it, and we have Hangouts for all the breakout sessions, and so it is pretty easy to attend from this continent. So please join us if you're interested. And I think that's all I had. So if anyone has any questions, if you'd like for me to go into more detail about anything, I'm more than happy to. Also, if you'd like a laptop sticker, I have a few of those down here.